Come back. Today I will discuss linear transformation as a review part. Today I will discuss different type of linear transformation. Just as a review, I will discuss whole concept as a review. I hope my all viewers have seen my previous lecture about linear transformation, and today I will discuss just as a review. We all of us know there exists a linear transformation T from one vector space to another vector space such that TUI equal to VI, where this UI means U1, U2 up to UN be the basis vector. Here I have considered here the domain is U, basis vector of U, and this VI means V1, V2 up to Vn is the basis vector of the vector space V. Okay. Our first example, find one linear transformation such type T be a mapping from V2 to V2, and here the basis vector of V2 is such type, the set containing 1 to 2, 1. Since here the base V2 to V2, obviously this is the basis vector of V2 also, this codomain also, and the mapping is such type T of 1 2 equal to 3 0 and T of 2 1 equal to 1 2. That means we have to find such linear transformation whose map is such type. Since this is the basis vector of the vector space V2, so obviously this will be the linearly independent set and span the whole vector space V2. That means any arbitrary point of V2 we can write it as C1 times 1 2 plus C2 times 2 1. Okay. That means this is actually C1 plus 2C2 comma 2C1 plus C2, which is equal to x1 comma x2. And obviously this is the system of linear equation. We can write this as 1 2 2 1, here the vector C1 C2 equal to x1 comma x2. Okay. And since this vector be the basis vector of V2, so obviously this system of linear equation always there exists unique solution. So obviously this linear transformation would be unique. Okay. Since this is the system of linear equation, so we can write this as augmented matrix 1 2 2 1, and here would be x1 comma x2. Okay. Then we have to find actually here the value of C1 C2. So after row reduction, just row equivalent from here would for row equivalent from R2 dash equal to 2 R1 minus R2, then that imply 1 2 here x1, here 0 minus 3, here x2 minus 2 x1. Okay. So from this matrix we can tell minus 3C2 equal to x2 minus 2 x1, that imply C2 equal to, that implies C2 equal to 2 x1 minus x2 over 3, and from this expression C1 plus 2C2 equal to x1. So just put the value here. So this would be C1 plus 2 times 2x1 minus x2 over 3 equal to x1. That means just after calculating C1 would equal to would be 2x2 minus x1 over 3. That means this is the value of C1 C2. Have you understood this calculation? Okay. By this method I have got the value of C1, C2 is here x1, x2 equal the value of C1 is 2x2 minus x1 over 3 times 1, 2, and the value of C2 is 2x1 minus x2 over 3, 2, 1. Okay. Now apply t on the both side, then this would be t of x1 comma x2 equal to 2x2 minus x1 over 3 times t of 1, 2 plus 2x1 minus x2 over 3 times t of 2, 1. Have you understood this method? Okay. And here given t of 1, 2 equal to 3, 0 and t of 2, 1 equal to 1, 2. That means this imply 2x2 minus x1 over 3 and here 3, 0 plus 2x1 minus x2 over 3 and here the t of 2, 1 equal to 1, 2. Okay. That means this linear transformation would be such type. Then after calculation, this would be, here would be 2x2 minus x1 comma 0 and here would be 2x1 minus x2 over 3 comma 4x1 minus 2x2 over 3. So after calculating, this would be 4 times 2x2 minus x1 over 3 comma 4x1 minus 2x2 over 3. That means here given linear transformation is t of x1 comma x2 equal to, here after calculating this would be 8x2 minus 4x1 over 3 comma 4x1 minus 2x2 over 3. This is our given linear transformation, and since here this linear transformation be generated by basis vector, so obviously this linear transformation would be unique. Have you understood? I hope my all viewers have understood this concept clearly. Okay. OS. Now I will see another linear transformation based on extension theorem. At first, as a review, just I will see what is the extension theorem. Extension theorem is every linearly independent subset of a vector space can be extended to a basis. And here the picture is such type. Consider this vector space V and consider there exists 6 vector which be the basis vector of the vector space V. And consider this be the linearly independent set of the vector space V. Also, these 4 vector be the linearly independent set of the vector space V. Also, these 2 vector be the linearly independent set of the vector space V. Here, if we can to add more 3 linearly independent vector, then we can tell this 6 vector be the basis vector of the vector space V. Also, similarly, if we can to add, there exist 2 linearly independent vector more, then by extension theorem we can tell these 6 vector also would be the basis vector of the vector space V. Also, if we can to add here 4 vector, not only 4 vector, 4 linearly independent vector, then we can tell these 6 linearly independent vector would be the basis vector of the vector space V. And this we can tell by extension theorem. Have you understood? I hope my all viewers have understood this geometry very clearly. Okay. Our next example is determine a non-zero linear transformation T from the vector space V2 to V2 which maps all the vector on a line x equal to y onto the origin. That means here all the point y equal to x maps to 0 vector. But here the question is determine a non-zero linear transformation Here the given instruction give all vectors on the line xy map to origin. To find non-zero linear transformation, here I will use the extension theorem. Here there exists more point in vector space which will map to obviously with the non-zero point, because here the question about non-zero linear transformation. To define linear transformation from vector space to vector space, I have seen in my previous video, we need a basis of the vector space V2. Here, define the subspace. Consider this subspace as a W, which be the maps all vectors which on the line x equal to y. Have you understood this subspace? And in this subspace, the basis vector would be such type 1 1. So, by extension theorem, we can extend this basis vector as a basis vector of the vector space V2. If we consider 1 1 and 1 0 vector, since this vector is also linearly independent, so this can be basis vector of V2, and the mapping would be such type, since 1 1 be the basis vector of this subspace, so obviously 1 1 maps to 0 0, and T of 1 0, since this is non-zero linear transformation, so obviously T of 1 0 map to on the non-zero point. So consider T of 1 0 map to same point 1 0. Therefore, since this is the basis vector of V2, so similar to before, we can write any vector x. Consider this is as x1 x2 be the arbitrary vector of V2. We can write this any vector be the combination of these two vectors. That means this is the C1 1 1 plus C2 1 0. That imply C1 plus C2 equal to x1 and C1 equal to x2. Okay. So from this expression, C2 equal to x1 minus x2. Okay. Have you understood this process? Similar to before. Now apply T on both sides, then this would be T of x1 comma x2 C1 times T of 1 1 plus C2 times T of 1 0. Okay. Now put the value of C1 and C2 here, then this would be x2 comma 0 comma 0, and put the value of C2 here would be x1 minus x2 comma 1 comma 0. That means T of x1 comma x2 equal to actually x1 minus x2 comma 0. Have you understood this linear transformation? Okay. Check here. If you put T of 1 1, then this would be 0 comma 0. T of 3 3, this would be 0 0 0 comma 0. But other point, if you consider T of 2 comma 4, then this would be minus 2 comma 0. This linear transformation is such type. I hope my all viewers have understood this linear transformation clearly. Okay. Now I will discuss one example based on system of linear equation. Today I have discussed this question as a review. Okay. Let's see the question. Now I will see one system of linear equation. Obviously this is basic question which had come C.M.I. PhD 2014 exam. But this question is based on system of linear equation. So as a review, I have chosen this question. The question is, consider AB M cross N matrix over the real field and consider one particular B naught belongs to Rm. Suppose that Ax equal to B naught has a unique solution, then which of the following statement is or are true? Option 1. Ax equal to B has a solution for every B belongs to Rm. Option 2. If Ax equal to B has a solution, then obviously this solution be unique. Option 3. Ax equal to 0 means homogeneous equation always imply unique solution if there exists unique solution of non-homogeneous equation for particular B naught. And option 4 imply A has rank M. Notice here A, B, M cross N matrix over the field R. That means obviously there exists a linear transformation A from Rn to Rm. Okay? And there exists a solution Ax equal to B naught, where B naught not whole B. Here B naught be particular element of particular vector of Rm. Have you understood? And for this B naught there exists unique solution. Now my question, if for particular B there exists unique solution, then that imply X equal to B has a solution for every B belongs to Rm. At first think oneself, then see my solution. At first just recall what is the Ax equal to B solution. Ax equal to B means obviously B is linear combination of this set a1 x1 plus a2 x2 up to an xn, where ai belongs to Rm. B is actually the linear combination of this solution, and the solution exists means obviously since B be the linear combination of this vector, that means this is actually the definition of column space. That means if there exists solution of non-homogeneous equation, that means there exists some x such that Aixi equal to Bi, B, where this B is actually span of the set A1 up to N, and suppose no, that imply B belongs to column space of A. That means if there exists solution of non-homogeneous equation, then that imply B always belongs to column space of A. And we all of us know the picture. This is the, at first consider the linear transformation from Rn to Rm. The picture would be such that this is the row space, this is the null space, and in codomain this is the column space, and this is the null space of A transpose. Have you understood the picture? And row space always map to column space, and null space map to only zero vector. Okay? When there exists solution, that means B belongs to this column space. But if there exists no solution, that means B does not belongs to column space of the matrix A. And if there exists solution, then B belongs to column space of the matrix A. And we all of us know the solution may be unique or may be infinite. Also we all of us know solution exists when we can write the augmented matrix such as A augmented B. If rank of the matrix is equal to rank of the augmented matrix, then there exists solution. That means when rank of A equal to rank of augmented matrix means B can be written as linear combination of A1, A2, An. If there exists solution, then two conditions. One, rank of A can be less than n, or rank of A can be equal to number of unknown. If rank of A less than number of unknown, then column space are not linearly independent, that imply. But if rank of A equal to number of unknown, then obviously this column space are linearly independent, and if linearly independent, then obviously this solution be unique solution. That means obviously this vector, since this is the linearly independent vector of column space, so uniqueness implies this vector actually the basis vector of column space of A. Otherwise, the solution will not be unique. Then this vector, when the solution would not be unique, then these vector are not linearly independent vector of column space of the matrix. I hope my all viewers know this concept. Let's come back our original question. Here has indicate Ax equal to B naught has a unique solution for this particular B naught. That does not imply Ax equal to B has a solution for every B belongs to Rm. So option 1 is the wrong option. Option 2 imply if Ax equal to B has a solution, then obviously this solution is unique. Obviously this option is true, because since here Ax equal to B naught, B unique solution has given, that means obviously this matrix is invertible, means all column of this matrix is linearly independent, okay, and this column vector be the basis vector of linear combination of this column space, okay. So if Ax equal to B has a solution, then obviously this solution also would be unique solution, because here A is m cross n matrix. Since Ax equal to B naught has a unique solution, that means obviously rank of the matrix would be number of unknown. That means obviously this would be n. So if there exists another solution, then obviously this solution would be unique. And Ax equal to 0 always has unique solution, because when B naught equal to 0, since the matrix is invertible, so obviously X equal to 0 has a unique solution. Option 4 indicate A has rank m. This does not true, because since Ax equal to B naught has a unique solution, that means rank always would be number of unknown, which is actually n, okay. So rank of A equal to m, this is not true. I hope my all viewers have understood this question. In my next video, I will discuss another topic of linear algebra. But at first, I will highly recommend you, please see today's video with pay attention, because I have discussed this topic as a review. If you see my previous video, then you will understand this question in better way, and by this question your concept would be more clear, okay. Thank you so much. See you soon. Stay safe and stay positive always.